Section 10.7.3 Adaptive Arithmetic Coding. Lempel-Ziv gives decent compression for any type of file because it is adaptive. Huffman coding and arithmetic coding give better compression, but only for files whose character frequencies match the underlying frequency table. There are several ways to make Huffman coding and arithmetic coding adaptive, and all of them make the corresponding encryption methods stronger. All such methods involve counting the characters in the file as you encode them. The more closely the character counts match the character frequencies in the file, the better the compression you get. You might think that you could just count all of the characters in the file and then use the actual counts. The problem is that Riva cannot count the characters in the file. Riva must use the same frequencies as Sandra, or she cannot decipher the file. The solution to this dilemma is for Sandra to count the characters as she enciphers, and for Riva to count the characters as she deciphers, so they will both have the same counts at all stages. All the character counts start at 1. If you know the frequencies of the characters beforehand, even if they are only rough estimates, you can increase the counts for the more frequent characters. For example, if you are using a 256 character set and you expect that messages will contain about 1% uppercase E and about 10% lowercase e, then you could increase the character count for uppercase E by 2 and the character count for lowercase e by 25, that is about 10% of 256. The initial range for each character is proportional to its initial count. For example, if the 256 character counts total 500 and the initial count for the lowercase e is 25, then E would get a range of 25 over 500, or 0.05. There are two basic methods for adjusting the codes, character mode and batch mode. Character mode is practical only for arithmetic coding. In character mode, each time a character is found in the file, its range and the two adjacent ranges are adjusted. One adjacent range when the character has either the first or last range. For the 26-letter standard alphabet, that means A or Z. Here is an example. Suppose the letter T has been encountered, and that the adjacent ranges belong to the letters S and U. This would probably not be the case for arithmetic encipherment. The mixed alphabet probably would not contain S, T, U consecutively in that order. Suppose the character counts for S, T and U are 15, 20 and 5, so they total 40. Suppose the ranges for S, T and U are 0.062, 0.074 and 0.024, so they total 0.160. This combined range is reapportioned in the ratio 15 to 20 to 5. S gets 0.160 times 15 over 40, or 0.060. T gets 0.160 times 20 over 40, or 0.080. U gets 0.160 times 5 over 40, or 0.020. Over time, the ranges for the characters will converge to the correct widths. Character mode works reasonably well with a 26-letter alphabet. It works very poorly with a 256-character alphabet. Most of the 256 characters will not be adjacent to any of the high-frequency characters, so their frequencies will remain static. This is particularly true for the standard ASCII representation, where all of the letters are clumped together. Batch mode works for both arithmetic coding and Huffman coding. In batch mode, the entire set of ranges is adjusted at specific points during the encoding. For example, the ranges could be adjusted after encoding 64 characters, after 128 characters, after 256 characters, and so forth. At each of these points, the entire range would be reapportioned according to the current character counts. This converges more rapidly than character mode, but between reapportionments you are working with old, unadjusted frequencies. In batch mode, it is possible to count the frequencies for bigrams and even trigrams. Bigrams or trigrams that occur more than once could be given their own Huffman codes or arithmetic code ranges. With this refinement, arithmetic coding will almost always give better compression than Lempel-Ziv. There is one problem with counting bigram and trigram frequencies, namely storage. With a 256-character alphabet, there are 65,536 different bigrams and 16,777,216 different trigrams. If storage is plentiful, this might not be a problem. If storage is limited, one solution is to count only bigrams and trigrams containing the most frequent letters. For example, if bigrams and trigrams were restricted to the 20 most common characters, then there would be only 400 bigrams and 8,000 trigrams to count. To determine the most frequent characters, counting of bigram and trigram frequencies could be postponed until some fixed number of single characters have been encoded, say 256 or 1024 characters. One way to accomplish these restricted counts is to count only single characters in the first batch to establish the most frequent characters. Count bigrams in the second batch using those high-frequency characters. Count trigrams in the third batch using only a high-frequency bigram plus a high-frequency letter. Once the high-frequency bigrams and trigrams have been chosen, they are given their own Huffman codes or arithmetic ranges. In other words, they are treated just like single characters. For arithmetic coding, character mode and batch mode are not mutually exclusive. You can balance the ranges for each individual character as soon as it is encountered, and balance the extended set of characters plus bigrams and trigrams at the end of each batch. When doing Huffman encipherment or arithmetic encipherment, at the end of each batch the alphabet should be reshuffled before the codes are replaced or the ranges are rebalanced. This is particularly needed if bigrams or trigrams have been added or deleted. This means that Emily will have a limited amount of material to attack before the codes change. For encipherment, it may be preferable to use batches of irregular length, say after 217 characters, then after 503 characters, and so forth, so Emily will not know when the codes change. One further refinement to adaptive coding is to divide all of the counts by 2 after the ranges have been rebalanced. This lets the codes adapt to situations where the character frequencies change. Older frequencies will have less influence on the ranges, and newer frequencies will have more influence. For example, suppose the text is a book of stories by different authors. Each author could have a different vocabulary or different subject matter, or even write in a different language. Of course, Sandra and Riva must agree on all of this beforehand, so that Riva will be able to decipher and decompress the message correctly.